accelerating, and AI is now also finding its places in critical, safety critical systems, law enforcement agencies, medical applications, and so on. AI systems are good, they are performing better, but they also make mistakes. And in certain cases, in fact, their decisions are not trusted by humans. Now, if a AI model tells us that, okay, some person has got some sort of critical disease or critical illness, obviously, we will be curious to know on what basis you are saying that, how long it is there, how it has crept up, and so and so. So this sort of questions. So this sort of questions are basically, this is what we call it as interpretations or explanations. So if we are with a physical doctor, the physical doctors will normally tells us, okay, these are the stages, these are the reasons, and so and so. But how the AI models are telling that, might be they can tell that the disease is at this particular stage, but on what basis? With what confidence? What are the evidences for that? So this is what we are talking in terms of the explanation. So there is a trade-off between the accuracy and explainability. The problem is if we go on improving the accuracy, the explainability starts to decrease. And if we go with say explainability, then we need to compromise with the accuracy. Like if we start with say the normal rule based systems where we had quite a good explainability because there were rules like if this and this and this, then we know that due to these reasons this condition is holding true. So those are the rule based systems. Now you think of if we have started from rule based system and slowly moved on, and now we are in the era of convolution neural network, deep neural network, recurrent neural networks, and so many. In fact, in general, deep neural network. So in deep neural network, we have a series of the layers, and on what basis the decisions are made, that is really difficult to understand. So that's where we need those sort of explainability. Now consider, say we are using the applications of AI in transportation, finance, security, legal, medicine, military, all these areas. Now the questions what a user may ask: why did you do that? So why did you make this signal red and this signal green? On what basis? What is the ground? Why not send something else? Why didn't you do or you took the different decisions? When did you succeed? When did you fail? Why can I trust you? How do I correct an error? And so on. So these are the questions which current generations deep learning models, or in fact some of the machine learning models also do not have. So that's where we are talking about explainability. And considering especially the medical cases, the safety critical, legal, security, military, finance, in all these cases. If you just say to a customer, so to a banking application, if a customer applies for a loan, and if you say that okay, your loan is rejected uh, because the system said so, or if the system says to you that okay, this customer is not reliable, obviously you will be interested to know on what basis you are saying that this customer cannot repay my loan. Because if the customer asks me, then I can tell him. Or in fact, for my own trust, or in fact for my own confidence, I should know that. In case of legal matters, why, on what basis you are suggesting this sort of say uh, some sort of scenario for this and so, right? Now what we are today, so today we are having some training data, we are having a learning process, we give this training data to this learning process, then ultimately we get a network like this, and then that network just says finally this is a cat. And it also gives us certain probability that at around 0.93 probability, or say with 93% confidence I am saying that this is a cat. Now the question is, why did you do that? Why did you say that? On what basis you said that this is cat only? Why not something else? And you might be wondering right now, okay, exactly. So system has told it has seen so many examples of cat, and then that's why it is saying it is cat. We human being also say do the same thing. It has been seen in several experiments. There was a very popular experiment where a distinction between husky, a breed of dog, and wolf were made. The system was performing quite good, above 90% accuracy was there. But when people started to investigate for on what basis it is making the decision, then they found that the decision is not made based on the shape and size and eyes and ears and nose of the animals. Basically, the decisions were made based on the background. That means whether there is a snow or not. If there is a snow, then most of the time it was told as a husky, because they were most of the pictures of huskies were from snowy area. So based on that snow, so whenever it was looking at the snow or it was finding some white area, it was saying that this image is a husky. So that's the problem with this sort of blind models. It can predict accurately, but sometimes it may not capture the essence. So it is blindly predicting. You can say by luck, the prediction is going correct. For the cases which have been shown to them for our training and testing cases. But you think of those models when those models are really deployed in a scenario. And in that scenario, if the background is different, so then that system is bound to fail. In fact, if you have gone through, one of the biggest failure of machine learning project was by US Defense. They developed a system to identify the intrusions, and their system was working perfectly and almost 100%. And it was declared a good success, and then finally it was deployed. When it was deployed, it was found that it is yes, its success is zero. The problem was the system was trained in daytime. So every image which was shown to that particular system was taken from daytime. And hence in daytime it was having the clear cut vision and it was able to identify the objects. But the real deployment was in the night time, because it has to daytime anyway it is visible. So night time it was thought to be that the automated system will work. But night time it was never working. So these can be one of the problems. These are the problems with machine learning and deep learning models, and hence we need this sort of explainability. So now, in terms of explainable AI, what we are thinking, so that's tomorrow. What we are trying to do, we are trying to, or the research community in fact is trying to develop new learning processes which will have certain explainable models. The models will be able to explain exactly why I am deciding that this is a cat. Like it can give you some output, like it has a fur, whiskers, and claws. It has this features, it has that features, and so based on that, if someone gives you that, okay, these are the features on based on which I decided that this is this, your confidence with that particular system will be quite good. And you can also, if your boss asks you, if your manager asks you, you can easily say that, okay, these are the reasons on which the system tells, and I also accepted that this is good. So that's where this explainable machine learning models are going to play their roles. That's what I was telling you, that in earlier models we had rule-based systems. So when we had that rule-based systems, so in rule-based system, we can easily say if this is true, then this. If this is true, then this. If this is true, then this. Hence, we were knowing why I am taking this, why I am outputting this particular output. But if we have a network like this, where we are giving some input here and we are getting some output here, something is done in this one. So this is totally a black box. So if it is a black box, what is going inside we do not know. We just give input, we get output. On what basis this output is coming is not clear to us. So they are, although they have improved the accuracy to a very good level. So they are good, quite good for accuracy, but they are not so good for accuracy. If I just make a a chart of say accuracy versus, if you just want else what you know, if you just draw, say this is my accuracy, and say this is the interpretability or explainability. Interpretability. Then you can say the neural networks will have the best accuracy, but their interpretation will be quite low. Whereas if you have a classification rule, so rule-based system, so rule-based system is here, it has got the maximum. Then probably you have the linear regression. Their accuracy will be slightly lesser, but they will have basically quite good interpretation. Then you can have decision tree, probably then k nearest neighbor, then support vector machine, and then random forest. So this goes like this. So if you see into this sort of diagram, this idea. So if you are thinking of interpretation, your older systems are good enough, but they are quite low on the accuracy part. So the accuracy is low, very low for this. If you strive for accuracy and if you go for neural network, then your interpretation is quite low. So now what we want, okay, given a scenario, what we want, we have two different, now we can go in a two different way. One is you build interpretable model. So build a model which is already interpretable. So build interpretable models, interpretable ML models. The second one is, okay, you have already interpretable, you already have some models, so you assign or you derive certain expression for these existing models. So these are the two ways derive interpretation for existing MLs. I hope I'm clear what I'm trying to say. In one case, either you go with some sort of rule-based system like this, or you try devise new ML algorithms which are inherently, intrinsically interpretable. Second one is, okay, we have some ML model existing already. So let us try to enforce or some sort of, by some mechanism, let us introduce some sort of, say, interpretability into that. Okay. So these are the two ways we are thinking. So one, there are several other definitions also, but we call it as like there are several terms which you will come across if you think of this. Explainability. One is called as model agnostic. Model agnostic. Model agnostic means we want to develop certain interpretability rule which can be applied to any model. Now we are coming to the second one. Okay, there are certain models, and then I want to add some interpretation or add some explainability with the model. So what or how I can go? So one way is I can develop some explainability technique which can work for all the models. So we call that technique as model agnostic technique. And in this particular talk, I will talk about two such model agnostic technique. One is called as LIME, LIME, LIME. The other one is called as SAP, SHAP, SAP. So these are two very popular model agnostic technique. The other one is called as model specific. So given one model, you develop something which can work for that particular model. Like you apply an attention for specific, say, a neural network. So specific type of attention in a specific neural network. So that is only for that particular neural network. So that can be some sort of model specific. Then you can have global explanation. Sometimes if you are going to give explanation, you can give global explanation. So my explanation is global. I will take care of all the available data set which is given to me, and then I will try to give an explanation for that. The other can be local explanation. So we can decide on a smaller data set and we can go with a local explanation. So Lime is basically a local explanation model, whereas SARC is basically a global explanation model. Okay. Now, having told that, what is XAI? So now I think by this time it should be very clear. So this is a system that explains the decision making is provided with a verifiable explanation that how machine learning system is making decisions. There are two ways I've already discussed. So this is how we have moved on. We have symbolic AI, statistical AI, explainable AI. Now we are talking of. So this was the black box approach. Now this is what we are thinking. Now, why these things are necessary and how to whom they can help basically. If we add explainability to the existing model, who can be beneficial or who can have say some profit or some advantage from that. So, if we have an explainable model, even the business owner will be benefited by. It can think of that. Okay, I can trust this AI decision because this AI decision is given with certain explanation, so obviously I can trust. I can influence the others, the investors or the customers of the businesses. Okay, this is how we are coming to this particular answer. Customer support. So if you suggested something to a customer and then customer asks that why you are suggesting this or why you are going in this way, if your model is a black box, probably you cannot do anything. But if your model is giving certain explanation, then you can support that. Your customer support unit can take that thing into so the confidence and help their customers to make them understand. The developers are basically IT and organization team. They can monitor and debug the model. So if the model is not performing well, if there is an error, if the model is malfunctioning, so where the error is coming from, which part of the model or which feature of the model is not working well. So if they can identify, they can probably rectify that and they can train or retrain the model on a better, say with the better features or the features can be better aligned and so on. For data scientists, so you can think of is this is the best model that can be built for my team and so. And again, there are other terms which I did not touch so far. Like there are several other terms of biasness and fairness. So you might have heard there is another very popular term which is coming into this current generation AI system, and that is of fairness issues. Fairness, bias, and so. So fairness is if a model is giving decision, how fair it is. How fair it means it is not making any racial decisions based on the race. Now it has been seen, in fact, in so many cases in USA, they have used the AI models in their law enforcement agency, and it has been found that for the same crime or same offense, in fact, a black people and a white people have been given different sentences or different verdicts. So for same offense, a white person was just given a fine of say $100 or $1,000, and then okay, let it go. Whereas a black was ordered say sentence of say imprisonment of say 3 years, and then along with a fine of say $5,000 and so on. So that's an issue of fairness which is creeping up, which is in legal cases of AI, which is one of the, in fact, you can say most talked about things, and a lot of work is going on. Like if I give you some word, Like if someone is, say, Mr. X is gay. So as soon as I say gay, basically that gives a negative sentiment about that. And any model will, if you take this sentence and if you in fact ask a model, any sentiment analysis model, what will be the sentiments of this word, which is a gay, then the sentiment will be negative. Now in several countries it's legal and so the question is why this sentiment should be so negative. This is basically an issue of fairness. This fairness is different from the explainability. Biasness, and this fairness is not coming, the system is not fair because of the biases, inherent bias which is existing in the system. And the biasness can be from the data, from the learning algorithm. Like if I say what is the color of, say, banana, most of us will say yellow, but there are green bananas also. There may be other colors also which we may not have, or which we have seen very less. So because when you collect data, probably you will collect more number of data from the yellow banana, or banana of yellow color. So your model has been trained with that. So that's a bias which is there existing in the model. So there are a lot of sample biases. The biases also exist in our social human society, and those same biases are also basically going into the AI systems. And a lot of, in fact we also are doing quite a good work in that bias, how to remove the bias. So one of the technique is you sample the data, so you properly balance the data, you remove some go through the data, and like gender bias basically is a very common term. So if you think a lot of things, if I say nurse, normally when you say nurse it will always be associated with say feminine gender, but male nurses are also there. If you talk of air hostess, now they are called it as flight attendant, so they are normally considered to be female. The system will automatically assign a gender, female gender with that. So these are the social biases which were there, and now they have already gone into the AI systems also. So most of the systems which have been trained, and people are now looking into those issues. So these issues are now coming up, and people are looking into it. So that's another issue. So whether are these systems decision fair, and so that also can be, if it is explaining on what basis I am doing something, then probably you can also reduce that, or you can also take care of that fairness. You can also decide that whether this system is going to give me a fair decision. So if, say, if a decision is made of a profession based on the gender only, then probably you can say that this system is not going to make fair decisions based on the professions. It will be biased somewhere, either with male or with female, because the profession should be based on the qualification and other things, not on the gender. So with this, I will stop here and I will directly go to the coding part, as I told you. So I think my screen is visible to you. Can someone confirm?
Yes, sir. Visible.
So if you have any question regarding that, or at any time, not the earlier one what I taught, or this one which I am going to explain, please interrupt me as and when you have a doubt, or you have a question, or you have something to say, because probably we can, that time itself we can discuss, and it will help everyone who is out here. So what we are doing here is we are trying to. So this is a data set which I have taken for this. So this is appliances energy prediction data set, which is available from ICS UCI. So you see Erwin Machine Learning Repository. You can see this data set, appliances energy data set. These are the details of this data set. You can download this data set from here. Although I am directly calling this data set from this particular website. So I am just calling this data set from this devs website. I have downloaded a copy also if you want to see. So this is the copy of the data set which I have downloaded here. So you see that one of the column of the data set is date. the other one is appliances, and then there are several variables like light, this is temperature, this is humidity, this is another temperature, humidity, and so on. So, in fact, if you read into this description of this data set, it says that this data set is at in this is the house temperature and humidity conditions, and it were monitored by Zigbee wireless sensor network, and they have maintained it. Although our target is not to talk about those Zigbee wireless sensor network and how they collected this. My target is just to show you exactly what, how fairness, how sorry, how explainability can be. I can show explainability with this particular toy data set. So here my output variable is the energy consumption. So the first column, which is the appliances, basically is the output variable or Y. Appliances, what energy it consumes in watt is our output variable, and so this is our Y, and rest others are X values. So these many X values, I think 27 such X variables are there. Okay. So if you make a linear regression will look something like this: y equals to say a0 plus a1 x1 plus a2 x2 plus so on. It will continue till the last variable. And we know that like a0 is the fixed general bias term. Then a1 is the coefficient which appears with the first term, like here t1. See from this data set. So with t1, say probably a1 is occurring, say rh1, with that a2 will occur, and so on. So if we implement a machine learning model for this, so you know that this is a simple linear regression, and we can solve it using so many techniques. One of the technique, obviously, which we prefer is the machine learning models. So with the machine learning techniques, with the data set which is available, we can find out the coefficients of A0, A1, A2, A3, A4. And once we have A0, A1, A2, A3, A4, A5, up to A27, we have solved this particular regression problem. And then you can say, sir, I have the interpretation. Yes, I also agree with that. With linear regression, you already have small interpretation available, because if someone says you exactly whether x2 is very important, is an important variable for me or not for this particular case, then you can say if this particular value is high, then probably x2 is going to play a very good role. If this variable is very, this coefficient is very less, then probably this x2 is having very less effect on this overall output y. I think that everyone agrees. So let me just implement this in the model, and I hope that this code is very clear to everyone. So we are here. We are importing a pandas a package, Python package called as pandas, and then in pandas we have a function called as read CSV, through which we read this data set. Since this data set is in Excel CSV format, I have already shown you. So we are reading this data set through the CSV command, read CSV command. Once we have read it, you see that the first column is date, which is not going to play any role in our overall task. So we are deleting this data set. So we are deleting this column, whole column, and then we are looking into this exactly what is there in this data set. So if I run this, you see that these many columns. So date is now gone, and we have the appliances to this R1, RV1, RV2. Right. These many things are there. If you want, you can see just the columns. How many columns are there? We have already seen this. So these are the columns which are available. Then what we are doing here is, if we are segregating, as I told, y is our appliance variable and others are x. So we are popping the appliance variable from this whole frame, and we are putting it into y, and rest is put in x. So if I run this code, and then if you want to print x, you see that this is how the x looks like. So we have this light T1, RH1, T2, RH2, T3, RH3, and so on. And these are the values corresponding to each and every instance. So 0th instance, this one, this will be continued. first instance, second instance, and so on. Here, if you see, I think in this particular code, I am taking only 100 rows. There are total 19,000 something rows in this whole data set, but this will take a long time to show you. Hence, I have restricted it to 100 rows. You can go with the complete data set. And then similarly, you can see the Y values. So if you print the Y values, you see the appliances values, which is 60, 60, 50, 60, and so on. So first 100 appliances. And then those who have done even the basic machine learning code, they know that in order to implement any machine learning codes like linear regression, support vector machine, logistic regression, decision trees, ensemble learnings like gradient boosting and random forest. And so what we need is we need a line to import this from sklearn model. So this command may look different for different models. So here we are using a linear model. So from sklearn.linear model, we are importing linear regression. And then we are creating an instance, basically an object of this linear regression. And once we have created the object, we are calling a fit function. Basically, this fit function is what is training. Fit function is what a training is. Whenever you see a fit function in any Python program, be assured that you are training there, and this will take some time to just fit. And in fit function, in all fit function, you have to pass at least two arguments. The first argument is the independent variables, that means x, and the second output is the dependent variable, that is y. So we pass on both x and y, and then once it is fit, then we just see the coefficients. So as I told here that a0, a1, so these are the coefficients. So these coefficients will be our output. See, so these are the coefficients. So lights, this T1, this RH1, this. So you see that this is very small coefficient. This is having very large value. This is having negative value. This is having again a positive value. This is having a negative value, and so on. So for everyone, there is a the bias term is not shown here. So these are the coefficients which we got. Now, as I told you, okay, you can say that this is explainable at least a smaller, at least a simple explanation is there, that if the coefficient is quite big and positive, then that means this variable has quite a big effect. Otherwise, this is. But this coefficients also depends on in what unit you are passing these values. So instead of this x, say somewhere you are passing this x as say days, and somewhere you are passing this x as say months, and somewhere you are passing this x as seconds, then these coefficients will change. So they will be big or small depending on what sort of units or what sort of quantities you are in, which quantity you are entering this. I hope I'm clear. Because if I give days, say probably 6 days, 5 days, 7 days. But if I give seconds, this will be too high. Then this will become lesser. And proportional to that, this will become lesser. So then, should we say that this is having lesser effect? It's not. The effect will remain same. But since this value become larger, this coefficient will become small. Okay, that's the problem with a normal normal linear regression model, and hence we need interpretation with that. So this is what I said. So for introducing interpretation, as I told, I will be going with two different techniques. One is called as SAP. SAP stands for Shapley's. Shapley's. So SHAPLEY. So Shapley is basically it's a game theory based technique. So what it does, consider that now Cricket World Cup is going on. So you consider that two teams are playing. Or say if you want to find out the importance of one player in a team, so how to find out? So probably you need to find out all possible permutations. If you remove one particular player, and then you see the performance of the team, then you remove another player from the team, introduce that player in the team, and so on. So basically you need to take all possible permutations, see the effect, and then you can come to a conclusion that okay, this player is, the importance of this player can be something like this. I'm not going into mathematics of that, but that's how the SAPLay values work. So there is a nice package in Python called as SAP. So what we are doing is we are importing SAP. Let me see if it works. Otherwise, we need to install it since it's saying no SAP is installed. So we can in fact write or install this pip install SAP. Since I'm running through Google Colab, so I'm downloading it, installing it. So once it is installed, now let me run. So now we are importing SAP, and then in SAP there is a function. So if you see SAP, so these are the, so this is the documentation of SAP. So see here, you can get everything which is related to SAP from this website. So there are API references, API examples. So you can take everything from this one. There are several functions available here. You see here. So SAP API reference. So there is SAP explanation, SAP explainer, SAP tree explainer, GPTU, linear explainer, permutation explainer, partition explainer, and so on. Obviously, you need to go through the details. Then there are several plots available in the SAP. Then there are several maskers. There are several models also, utilities also, data sets are also, some data sets are also available which you can test with them. So here we are using or calling sap.expander, and then we are calling model.predict.x. So it will take some time, and that's why I have taken this number to be very small. And then you can find out once this explainer has been trained on this, then you can see the SAP values. So it will calculate the SAP values as I told that you want to create or you want to calculate the utility or say a value of each and every player. So basically this will create the SAP value for each and every one. You can see the SAP values. SAP values. So these are the SAP values. So you see, say for 99, so for there are 99 instances. So for all 99 instances, it will create values. So what we are going to do here is we are taking 20th instance. 20th instance means basically if you see the 20 number rows, this one. I think 20th instance will be this one, sorry. This one, because first one is date. So this data set we are taking, and then we are trying to make references according. So then we are showing a partial dependence plot. Let me just plot this and then I will explain. So you see exactly what is happening here is, so this is the average of all the 100 data sets. So since there are 100 data sets, so with 100 data sets, this is the average effect of the power consumption. With lights only, this is the effect. Now with for 20th data set, if I say, then we'll see that for 20th data set, the light value is slightly higher than the average one. See, the light value is basically 30 here, which is higher than the others. So there are several 10 values, which is higher than. So on an average, this is higher than the other nearby or other data set which is there in the group of 100. So this is what a partial dependency says, a partial dependence plot says. You have other plots also. Let me just show you this plot. This is really interesting one. This is a classical plot called as waterfall plot. And see here, again, this is with the 20th sample. This is sample ID is 20, sample ID, which is already defined here to be 20. So that's what we are working. Okay. So we are going with reference to that. So here it says that again, so the fx value is 98.883, and this is due to, so what it is doing is it is saying that T out has an effect or the importance of predicting it 98.833 as the final value for this energy consumption or energy. T out is having an importance of 6. The most important is RH out. You see here, it is adding so many values, and the importance, the total absolute value it is adding is 87, and this is the total positive value it is computing, and so on. So you see, some of them are positive, some of them are negative. So these are the value which are really important. These are the positive important one, and these are the negative also important one, that they are decreasing these values. So they are influencing in fact. These are the other way you can see the importance of the different features. So you see that these are the overall, for the overall average features for all 100 samples. This is one of the most important variable, T out. Next important variable is T dew point. Next is RH out, and so on. So these are the different values. You can again plot the same thing in a bar plot, and you see that this is how it works. These values are different because earlier I trained with a different number of samples. So now it is coming out exactly same T out. So this is T out. This is another plot which is called as bee swarm plot. So, so you might have seen the earlier diagram. It was quite dense. Now, since I have lesser samples, 100 samples only, so this is becoming quite dispersed now, and the order also has changed. This is another diagram called as the heat map. Here, in fact, only I have 100 variables. So this is the heat map again. So this is one where we have the numerical output. This is the line, as I told, that I will be going with two different techniques. The other one is SAB, the other one is line. So in the same way, we can call the line. So we put line tabulator, and then line tabulator explainer. So let me install line first.
खत्म हाँ
ना क्या
वीडियो हाँ वीडियो लगी हाँ
ना
वीडियो लगी
And then you see, so with line, if I explain, so this is what the predicted value for a sample number 60, say is this one. Why? Because this RH is positively impacting it, and it is contributing a value 122. T9 is contributing positively, R this 3 is contributing positively, and so on. These are contributing negatively. The feature values, again, these are positive and these are negative. This is a local model. I mean to say, if I'm talking about 60, then it will consider the instances which are near to this, and then it will just try to make importance or make explanation out of that. This is with text. So this is with numbers only. One more example I will give with text. So I have to run through very quickly. So those who have worked with text, so or let me just skip this one and go to the image part. So this is an image one because that is more visually appealing and you can use it more frequently. So what we are doing, we are just calling the scalar IO image read and mark boundary and so on. So these are the image functions I am just calling. We have certain functions to load the image and process PGG images, and then we are loading one image which is there in my Google Drive. This is oka2.jpg. So this is the image. Now the question is what I was talking exactly on what basis, if the model is predicting it is to be oka2, on what basis, whether it is looking at this
ये सब
bird
पीछे
or
दे
it is looking at some background and then looking at something. So to do that, we use a technique called as segmentation. So we segment the image to several parts, and then we try to and the segmentation technique which we are using is Fulgent Pol, and it segments, it has segmented, so it will segment the image something like this. So let me apply this on this image, and you see that this is the segmented image. So now you can see that if the model has to identify, then the model has to look into this part, this part, this part, this. So these are the parts which should be the point of interest to us. And then let's see some of the segments. So these are some of the segments. So there are several segments. Some segments are highlighted here. So you see that segment number 11, 28, 16, 55, 56. So they have been highlighted here. So these are the different segment numbers. So just this part of the code is just showing that, okay, we can isolate these segments. So you can see segments 11 is might be this one or this one. That number is, I have not checked. We can check. And now let me just show you how this inception D model, if it works, how it works. It may take some time again. Okay, fine. And then inception is classifying this prediction class to be 89 and this one. Now let's see exactly explainer how it is explaining on what portion I looked and then I explained. Sorry, I decided. So my explainer will tell me, okay, this decided to be the prediction class is 89, which is this bird. It took some time. So have any one of you tried this technique earlier or tried this models for explainability? Anyone? Will anyone try this? No one. Well, this is Google Meet, so anyone can unmute himself or herself and talk. I do not think that this is a very restricted environment like Zoom or those. It is
Yes,
Webex
sir.
and so
Obviously,
on,
we will
where you
try.
can't unmute yourself.
Sir.
Have you tried any
Yes,
sort
sir.
of technique like
Uh,
this? Good.
so,
So this thing say, even if you are making prediction, if you want to check that if something is wrong, so why it is wrong, on what ground it is classified as, or it is marked as wrong. So you can just look into that. You can apply a line technique there, and you can see on what ground it was classified or it was marked as wrong, so that you can really improve on the feature part and the model itself, right? And now, in fact, now most of the papers, there are 2 3 ways of publishing paper nowadays. If you are working in text, then LLM is the option nowadays. So everything is coming to be large language models. If you are working with simple machine learning model like steel or those sentiment analysis and so on, so then this can be another say, addition to your work. Like right now, if someone just writes a model which will give you sentiment analysis of something or emotion of something, it's really going to be very hard to be accepted, because the literature is already floated with so many papers and so many ideas that anything you do might be there, already there. So yesterday it was better. I do not know exactly mistaken. By the way, let it be finished. So this is what, if you see the temporary and mask and explanation exactly on what basis it decided. So these are these highlighted area is the area which was looked by the model. So the model looked into this area. You can say the model concentrated on this area, and based on this area, it has decided that this is a particular part. Okay, that's the idea. You can in fact, if it runs, then I can show you. So you can in fact, here I have taken 15. You can improve on, or you can change these numbers, and then you can have different features. The number of, because these are the segments. So if you improve, or if you say reduce, or say increase the number of segments, the number of features, and the area will also change slightly. I don't know exactly why it is taking so long. So, okay, so okay, now this has been already finished. So let me see again. Just run this. So if I just run it, this is the same diagram which I have already shown to you. So this is what. Now since today the segments were different, the area is slightly different. So instead of 15, if I make it to be 20, so you see, so it has looked into this. If you want to make it lesser, you can know I do not want to make too big. I want to make smaller only. My concentration or my decisions will be very small, confined one. If you make 10, it's this one. So you see that more or less it is looking at the birds area only, although it has taken slightly the other areas. That because of this segmentation nature, it has to, because in that segment, in that uh, big segment, no, so there were the other, this part were coming into that segment, so that's why it is taking that bigger segment. But otherwise it is looking into this bird and this as a whole, and then it is deciding. Okay, so that's all. There was one, if you allow 2 3 minutes, I can just show you this NLP part also, okay, how it can be used in the natural language text also. Can I take 3 4 minutes? Okay. So if some of you have worked in, are working in the text area, then uh, we are just taking, this is a toy example again. So we are taking the IMDb data set. So just run this. We are taking IMDb data set, and we have a corpus there. We are deciding our, the partitioning this into train test split, and then fitting it to the vectorizer part by fit transform, and both test and train. So we do that, and then if you want to see the corpus, what was there in one of the sample, so this is what you see, that this is one of the review which was given. And if you want to see the Y part, this is the Y part. Now, if I learn a logistic regression for that, whether the review was, or the movie is good or bad, so sentiment is positive or negative. Basically, that's what it is doing. So whether it is a positive sentiment or negative sentiment. And then if I run this SAP explainer on this one, you see that these are the words. This is although a very small example, very teeny example. So these are the words, in fact, and bad. You see that bad has a very big effect, negative side effect, very big effect. Of this sample is negatively marked, and this bad is playing quite a big role. Great is playing a role, but not so bad, because bad is having too big, so this should be negative. It, BR, worst, no, was, do's, all these are having negative values. You, will, these are some positive values, and overall, this review was considered to be negative. So this is how basically you can Although this is very small and teeny example, the uh, nowadays no one works with this vectorizer and fit transform. Everyone goes with the embedding technique. So if you go with those embedding techniques, probably we'll have much better. But this is how you can say that on this basis, I classified or I told that this was the result. Okay, so to conclude that, so we need explanation to all pre-developed AI models, and we can have there are already multiple methods have been proposed, but still a lot of work has to be done. The existing models already vary in terms of explanation target, explanation diverse, family, and so on. Still a research active area of research with new and improved method, which needs to be developed consistently, and such diversity of choices can make it challenging of explainable AI experts to adapt to the most suitable approach for human application. Okay, so that's all from my side. Any question or any suggestion or any point from your side? And I'm really sorry that I need to take help of pen to write a lot of things. Although with mouse, my writing is very bad. I agree. So because of my bad health, last 10-15 days, I could not make the slide. My focus was okay. Let me just give you certain coding so that you can at least you can start with. So the slides were not too good. They were made by one of my students, and she missed a lot of things which I instructed her. So I'm really sorry for that. Any comment other than that, writing and those slides is welcome.
If anyone have any question, please feel free to ask, sir.
Okay, so there is a question: how do SAP and Line handle different types of machine learning models, such as black box model or deep neural network models? So that's what I just demonstrated you. Like SAP, I already told you. So this is the SAP. Uh, Although I explained SAP with the help of a linear model, with simple regression model, but you see that SAP can support these many models. SAP, sorry. These many models are there. There are transformer pipeline also. There are top KLM model, masked LM, text generation, teach forming, and there are so many models of SAP. And then this works with. There are several explainers like permutation explainer, GPU explainer, additive explainer, deep explainer. So you see. So if you are working with those sort of models, instead of just calling here where I have called, like here I have called explainer equals to sap.explainer. Instead of this, you call sap dot say deep explainer. That's all, and then you pass down the appropriate data. And for again, that the question was for different deep learning, and so all are black box model. We are considering them to be black box. That's why SAP is model like model. That means it can work with any model. So these are all different models with whom SAP can work. I hope that's clear. So please have a look at this what is called as documentation pages of SAP. This is available on this site. Okay, and you will see supporting codes also. Exactly, if you want how with deep learning models, how I should use. So if you click onto this, probably you will get all the reference. So class, deep resembles model, then data, then session. These are the inputs which you need. So these are the parameters which you need to pass, and these are the methods which are available in that with that particular set models. Okay. And same thing for lime also. You can find out for lime also if you see lime documentation. So this is lime documentation. So similarly, you can check with lime how many packages are there, what are different modules, and what are like image module, tabular module, text module. So these are the modules with lime, and you can use with that. So here, if you see that first we are trying normal model. So we tried with normal model, that's working well, and with that normal model we are explaining. So we are not now not training any new model. We are just using that existing model, and the SAP is only explaining exactly if it is predicting this X to be this, why on what basis and what ground. And okay. Any other observation point? It seems there are no more points. Although I had to because the time was usually what happens, no, earlier time was not mentioned, so I'm really sorry for putting so many things. One thing was normally usually